last week was about circles, and this week is going to be about polygons. And with polygons, I just think of it as just like straight lines, geometry with straight lines mostly. So if you have questions at any time, feel free to ask. And yeah, then we get started. So the first, like most basic kind of shape when it comes to this geometry with polygons is a triangle. So in this table here in the notes, I've kind of, well, I didn't really make myself, I just found it, but it's like just a table of key lines and points within arbitrary triangles and their properties. So the first one you see here is the perpendicular bisector, and that is just the line that is perpendicular to a side of a triangle and bisects or passes through the midpoint of that side. And basically, you can see here the point of concurrency means just that these lines for each side will intersect at the same point. And the same point is going to be the circumcenter of the triangle. And this kind of, this property kind of exists because for any circle, and if you draw a triangle inside, then you know that when you connect the radii to the vertices, the altitude from the center to the side length or a chord of the circle is going to pass through the midpoint because that triangle is isosceles. So that means that this altitude from the center to a side length is also a perpendicular bisector of the side. So sometimes when you're just constructing points or just diagrams, just know that the intersection of perpendicular bisectors of a triangle is the circumcenter. All right. So next up is angle bisector, and the angle bisector is quite literally the line from the vertex to the side that cuts the angle in half, so that each angle formed is equal. And this has multiple cool properties, which we'll go into a little bit later. But for now, just know that its intersection, or the intersection of all three angle bisectors of a triangle, is at one point, it's called the incenter. And we talked about this last week. The incenter is the center of the inscribed circle of the triangle. And the reason why this works is because of the two tangents theorem I talked about last week, where if we draw the incircle and pretend that this is tangent here, then simply just dropping the altitudes and then connecting to the vertices like this, you have the radii are the same for the circle, and then like you can think of like this length from the tangent point to the vertex is the same as this one from this tangent, from like this vertex, this bottom vertex, to this tangent point here. So then like these two right triangles are congruent, meaning that the two angles here are also congruent, which means that this line from the vertex to the incenter is going to be an angle bisector. So if you ever hear intersection angle bisector, you know that just refers to the incenter. And this is a very useful property. So next is the median. And the median is a line from the vertex to the midpoint of a side. And the intersection of all the medians is called the centroid. And the main point of the centroid is that it splits up the median into ratios of 2 to 1, where the 2 is closer to the vertex. So if we draw the three medians, like so, And let's just call these points like A, call this intersection point B and this midpoint C. Then you know that AB is equal to twice of BC. The ideal quality is low. All right, well, see if, is it better or is it still the same or worse? All right, okay, well, can everyone at least hear what I'm saying? All right. Well, if it's not very understandable, you can let me know. All right. Well, with the medians, I don't think the proof of the y is split into 2 to 1 is going to be like within the scope of this course. So just know that this property exists. And that's really the only thing you have to relate the median to anyway. And lastly, we have the altitude, and that is the height from a vertex to a side. So just draw a perpendicular line, and the intersection of all the altitudes is the orthocenter. And you don't really see this point used often at all because it doesn't really have any special properties, like at this level at least, besides just being the intersection of all the altitudes. So if you see orthocenter, just think altitude, and that's really it. The orthocenter is where all the heights meet, and the centroid is where all the medians meet. You can see in the table right here, they're written where, and yeah, this is just a common vocabulary, you could say, for geometry. So yeah. Okay, so now this is just basically just names of lines and points and stuff for actually any triangle. So just know that these properties still hold for any triangle. So we move on to the angle bisector theorem, which basically plays off of the angle bisector that is the second one on the table. An angle bisector theorem says, if you look at the diagram, here we have angle bisector, and A, B, C, D are all referred to the side lengths. Then you have A over B equals C over D, or A over C equals to B over D. And this kind of just, you can think of it as just the two sides on the same side of the angle bisector are in proportion, like to the other two sides. And I guess this property is used a lot, so it's good to know. The proof of it is actually using law of sines, which we'll talk about right after this actually. But so if you do want to know why it's true, you can actually derive that. So after the angle bisector theorem, we go to the common trigonometry theorems for triangles. And I'm kind of assuming here that everyone has a basic understanding of trigonometry, as in just the definitions of sine and cosine. So does anyone have like any questions regarding what sine and cosine are, or can I move past that? All right. So I think I'm just going to go over just the definitions a little bit. With sine and cosine, you most generally see them in right triangles, and they can be used for any angle. So the sine and cosine are functions of angles. And so if we have this angle here, we can call it alpha. We use Greek letters for angles for whatever reason. The sine of alpha, and let's call these side lines A, B, and C, is equal to A over C, and the cosine of alpha is equal to B over C. Yeah, alpha is the logo of Alphademic. Yeah, clever observation. But yeah, so yeah, and the cool thing about this trigonometry is that it only depends on the angle measure. Doesn't really matter the size of the triangle, the side length. This ratio for when you form a right triangle and the angle is one of the angles for right in the right triangle, this ratio stays the same no matter what triangle you're using. So basically each angle measure has a unique value for its sine and for its cosine. And unique as in the sine function will only produce one value for that angle. So two angles can have the same value for sine and cosine, but no angle can have two values for sine or two values for cosine. So that's the basic idea of that. So like the two most commonly used trigonometry related theorems for triangles is the law of sines and the law of cosines. And then you can see they're written right there. Law of sines states that the ratio of the side and to the angle it's facing, to the sine of the angle it's facing, is equal for every side in the triangle. And the law of cosines is kind of like Pythagorean theorem, actually, but it states that for any triangle, you can find the length of a third side if you know two sides and the angle and an angle. And this also works in reverse for law of cosine. So if you know all three sides, you can find the cosines of all the angles as well. I won't be going over how to prove the law of sines and law of cosines because I think that's kind of more advanced trigonometry. So if you've never seen these before, that's fine. Just try to remember them because they are used a lot for, I guess, higher level or just in the future. And a lot of key theorems do kind of branch off directly from these. All right, so is that kind of clear? Okay then. So next would be the sine area formula. And this is one of the, I think one of my favorite ones, where you can find the area of a triangle with only two side lines and the angle between the two side lines. So it says that the area of a triangle where you see everything's marked, the side lines are A, B, and C, and the angle in question is angle C. Area is 1/2 of A times B times sine of C. And this kind of works for, again, any triangle. And I will be going over why this works. It's actually pretty intuitive, where I guess, is sine an actual number? Well, sine is not a number. Sine is a function, and it's a function of an angle. So you'll never see just sine by itself. It'll always be followed, sometimes in parentheses, sometimes not. But like this, like C or the angle is kind of implied to be the, you could think of it as the argument of the function, or like what you'd put into it. And it returns a unique value for that angle. So does that make sense? Or again, I kind of went over it here too. Okay. So yeah, if you don't completely understand sine and cosine and trigonometry, you can kind of review that by yourself later as well. And then, okay. All right, with the sine area formula, this comes directly from just drawing a perpendicular from B to AC. And if I can draw a straight line like this, note the area of this triangle is just going to be B times this height H over 2, because it's base times height over 2 is area of a triangle. And this height can be written as A times sine of C. And this is because from the definition of sine is going to be in this right triangle that was formed from the height. The sine is just going to be the ratio of H over A. So we multiply A by the sine, that's just equal to H. So after that, all you would do is substitute this into here, and you get exactly 1/2 AB sine C as the area of your triangle. Is that cool? And this works. I'm going to show this for obtuse triangles too as well, since the height is not inside the triangle, it's outside. So we have the side lines are like so, AB and the angle C. The same thing is if you extend the side out this way and then drop a height to this extended side length, the area is still going to be base times height over 2 from the triangle, and you would have H is equal to A times the sine of 180 minus angle C. And basically with sine, it's a property of the sine function that the sine of the supplement of an angle is the same as the sine of the angle. So that would mean sine of 180 minus C is equal to sine of C. So then that also gives the same result. So that would be why this formula works for both acute and obtuse triangles. All right, so does everyone follow that? This is a lot of stuff. Okay, well, next up is Stewart's theorem, and this one can sometimes, if you're looking for it, it can kind of solve problems directly, where you can, for any triangle, so this is just an arbitrary triangle, and I label the side length as so, where the full side length, this full bottom side length is A, and N and M are the two segments that are divided at this point. And it basically states that there is a relation between every single side length in this picture. And it's that, well, I've written it, it's B squared times M plus C squared times N equal to D squared times A plus M times A times N. Or I like to refer to it as this, man plus dad, bomb plus sink, or CNC or whatever. But the idea behind it is that like you take each of these sides and multiply it with the opposite. Like you square both these sides, multiply it with this opposite segment, and you add them. And that's one of them. And the other one is kind of this Cevian, or just the point from the vertex to the side length times opposite side, then again. So well, either way, this is kind of a little, it's kind of difficult to remember at first. So if you like use it, as you use it more, it will kind of stick in your head. And this one seems kind of random at first glance, because there really doesn't seem to be anything holding like the equation, the sides together really. And the idea behind this is the law of cosines, and it takes advantage of the fact that these two angles are supplements, and the cosine of 180 minus an angle is equal to negative of the cosine of the angle. So you can actually use law of cosines using both of these angles, and eventually it does simplify down to something like this, to the Stewart's theorem. So just know that Stewart's theorem is a direct application of the law of cosines. Again, I don't think it's very necessary to know all the details behind it. Just maybe when you're doing problems, just try to see if this is ever useful. So you don't have to remember it right away. Just try to keep in mind. No, he did not invent cosine. I don't know who did. He just made this theorem, I guess. So, but yeah, it's just called Stewart's theorem. I don't really know anything more than that. So yeah, just another cool result from law of cosines. Yeah, okay. So I think that was all I wanted to do for triangles. So I think next we're doing quadrilaterals. And with quadrilaterals, there are a lot, not a lot, but there are a couple more terms you have to know. The two main ones being convex and cyclic. Convex means that no angles are greater than 180. It's for any shape, but so something like this, it would be a convex quadrilateral, and most problems do work with convex shapes. And concave, or the opposite of convex, would be something like this, where this angle right here is greater than 180 and it caves in. So a convex shape is just one that does not cave in anywhere. And next one is cyclic, and that one just means that it can be inscribed within a circle. And these are actually probably the most important quadrilaterals you'll see, like ever. So that's later. There's also a parallelogram, which is where opposite sides are parallel, and that also means that opposite sides are equal length. And for a rhombus, it's a parallelogram where all sides are equal. So you have a parallelogram, would be like this. A rhombus would kind of look similar. It's just all sides are the same. So it's a parallelogram with equal sides. Sure. And a rectangle and a square, I'm sure everyone knows what those are. And lastly, you'd have the trapezoid and the kite. So a trapezoid is this, where you have one pair of parallel sides and two non-parallel sides. And the kite, which looks like a kite, where the diagonals are perpendicular, and you have two adjacent equal sides like that. Again, these are more less commonly seen. So yeah, those are just the definitions. The next is cyclic quadrilaterals, and these become useful because it's another way to like implement circles within like your geometry problems without it seeming too relevant. And the most important aspect of a cyclic quadrilateral is that opposite angles add up to 180. So angle A plus angle C is equal to 180. Angle B plus angle D is equal to 180. And basically, this is true because of the interior angle theorem. Because if we draw like a diagonal such as BD, you have angle A faces this arc BD on this side, angle C faces this arc BD on the other side. So it faces the minor and major arc of B and D respectively. And each of A and C are equal to 1/2 of the degree measure of the respective arcs. And the two arcs add up to 360 since it's an entire circle. So these two angles must add up to half of that, or 180. So that would be why opposite angles add up to 180 in a cyclic quadrilateral. All right. And this becomes actually pretty cool when you can like make quadrilaterals when like the circle isn't actually part of the problem, but you can see that a quadrilateral is cyclic based on opposite angles or other properties. And then from there, you can use properties of circles to continue your problem. I don't think we have an example of that because we usually see that in Amy instead, or yeah. Next up is parallel line interactions, and yes, this is kind of basic, but I just labeled that angles 1, 4, 5, 8 are equal, and angles 2, 3, 6, and 7 are equal for parallel lines where Q and I don't know, M are parallel. That's not Q, that's L. L and M are parallel, and N, or the transversal, is cutting through both of them. And again, this is not very difficult. It's just something that you want to remind yourself of in case you do have parallel lines in the problem and you're just angle labeling, so that you can see congruent angles somewhere or similar triangles. So basically just know that these angles are going to be equal so that you can spot them in diagrams. So beyond triangles and quadrilaterals, there are lots of other polygons, and they just have a lot more sides. And usually with them, most of them that you'll see are going to be called regular, and that means that the sides and angle measures, so basically like each side length and each angle, they're going to be the same. So for example, if you're told a regular hexagon, which comes up a lot, it would look kind of like that, but it would be symmetric. And same with any of these shapes. So pentagon, octagon, like I think that's kind of the gist. And the main thing to know about polygons with more sides than 4 is how to find the total angle sum of the polygon and the angle measure of each individual angle. And basically for any n-sided shape, the total angle measure or the total angle sum of that shape is going to be n minus 2 times 180. And the reason why this is the case, so why do all the angles add up to this? This looks kind of random. Okay, well, I did get a question. Why does that individual angle degree change slowly decrease? And I'll answer that a little bit later. So I'm first going to get to this what the total angle is. So basically for an n-sided shape, I'll use a hexagon for example with 6 sides. You can split it up into 4 triangles like this. And we know each triangle has 180 degrees. So you just count the number of triangles in here, and there are 4. So 4 times 180 has to be the sum of all the angles in the hexagon. So that's really it. You count how many triangles you can divide the shape up into, and times 180, and that's how you find the angle sum. So for regular shape, you just divide by the number of angles you have since they're all the same to find any individual angle. And in this table provided are the angle sums and individual angle measures for the first 12 polygons. So up to a dodecagon with 12 sides. And you don't really need to memorize any of this since each of them can be derived just from the formula. It's just a reference sheet. And someone noticed that the individual angle measures are decreasing slowly. So like this difference, or not decreasing, they're increasing slowly. So like the differences are like 12 and this is kind of just like 5 and 4. And why is it like decreasing slowly? And the reason that's the case is we can consider how the angle measure is actually found. And that is by going n minus 2 times 180 divided by n. And for any n, if we plug in into this expression, you'll get the angle measure. So since 180 is a constant, it doesn't really affect the rate at which this would change as n changes, but this is just n minus 2 over n times 180. So this n minus 2 over n fraction basically determines the angle. And as n approaches infinity, we know that n minus 2 over n will approach 1, or the angle approaches 180. But it will never like reach 180 because at infinite sides, that would just be a circle. So there would technically be no angles. But so like with polygons that have like thousands or millions of sides, it'll look almost exactly like a circle. And again, n minus 2 over n as a fraction, as n goes larger, the difference between consecutive terms will be smaller. And this is kind of because you can think of it as like tapering off, or how since the difference between the numerator and denominator remain the same, but their ratio will just keep on increasing, but like, or it's kind of like how if you have the numbers like 1/2, 1/3, 1/4, and so on, the difference between these neighboring fractions gets smaller and smaller. So to, well, actually it's directly related to this. You know how 1/2 minus 1/3 is greater than 1/3 minus 1/4, is greater than 1/4 minus 1/5, and so on. Each one of these values are just n over n, or 1 minus 2 over n. And since this 1 over n gets smaller as n gets larger, 2 over n gets smaller as well. So then each time when you're subtracting a smaller amount, but you're also like decreasing relative to the previous one less, which is why the angles you can see kind of taper off a little bit, where angle measures for larger or more sides are going to be closer together than angle measures for the ones with fewer sides. So I hope that answers your question. But yeah, that's more like kind of like turning it into an algebra problem. Yeah, besides that, next is similarity. And similarity usually refers to triangles, but it can refer to any polygon. And with similarity, all it really says is that these two shapes have the same angles, or of corresponding angles are all the same, and the ratio between the sides are going to be the same. So like with two triangles, like if you draw a smaller triangle and a bigger triangle, and they're similar, that means their corresponding angle measures. So I already drew them so that they're kind of aligned, are going to be the same, and their sides, the ratios between sides are going to be the same as well. So this side to this side is the same as this side to this side, and this side to this side. And the cool thing about similar triangles, or any similar shapes in general, is that you can find the ratio of the areas as well. And the ratio of the areas is going to be the square of the ratio of their side lengths. So if the ratio of the side lengths is r, then the ratio of the areas is r squared. And this is because the sides are proportional, so their heights are going to be proportional with the ratio r as well. So since area is kind of like we multiply both of them, you're multiplying by r twice to get the ratio of the areas, so it's squared. And for the same reason, when you have similar solids or three-dimensional shapes, which we'll get to next week, or maybe in a few weeks, I'm not sure. The ratio of their volumes is cubed of the ratio of the ratio of their side lengths. Again, since 3 dimensions has you multiply by 3 different like side lengths, so that's why it's cubed. The main purpose of similarity is to write proportions and solve for unknown lengths. So yeah, I think that was all the major concepts that I wanted to go over. So next would be strategies. And when you're approaching geometry problems, I think it's important to look for right triangles, similar triangles, and isosceles triangles. And basically these triangles all have some kind of special property that you can use, such as well, the 90-degree angle and Pythagorean theorem for right triangles, the corresponding sides and angles for similar triangles, and the equal sides and equal angles for isosceles triangles. So after that would be angle chasing, which is just trying to figure out the measure of as many angles in your diagram as possible, since more information will generally help when it comes to solving problems. And for finding areas or problems where you're asked an area of some kind of shape, you can try to dissect that shape into smaller shapes that you know how to figure out. So I think the best example of this is a regular octagon, which is an 8-sided stop sign, basically. And the way you would find the area of an octagon, well, there are multiple ways, but you could divide it into these shapes like here, where you have 4 rectangles, a square on the middle, and 4 right triangles on each corner. So then you could find the area of each of those pieces, add them up, and then that's the entire area. Is the square twice the triangle? It is not twice of the triangle. That you can't assume that because I'm not entirely sure if I want to go over this, but for octagon, the sine is 1 and the angles are 135. And since these are all right angles that happen to be present in a regular octagon, this is 90 and this is 45. So then this hypotenuse of the triangle is 1 and the sides of the square is 1. So they won't have the same side length. So it can't be half the area. It would actually be, this is root 2 over 2 as a side length for this right triangle. So yeah, you can't really assume anything. You actually have to figure out from like what you definitely know, then go from there. So if you want to try out finding the area of an octagon, feel free. I don't think I really have time to do it today though. So yeah. So the next tip would be to drop altitudes and draw other important lines. And this comes kind of similarly to connecting the centers of a circle to important points. Just try to get all your points like involved in the diagram. And lastly, identify what the problem is asking for and what information you need to solve the problem. So like, don't try to do any more work than you really need to. And sometimes the answer is just easy to find when you have a set goal in mind. So a lot of times you can work backward, like from what the answer is asking for. So how would you find what the answer is asking for? Well, if there's something else you need, then try to figure that out first. So like work backward from how you would get the answer until you get to a point that you actually know how to like solve. So yeah, work backward is what I'm trying to say here. All right, so that's it for the lecture parts. So we just have some problems, and I apparently didn't label any of these with stars, so that probably means I didn't remember to. So we'll probably just go in order here. Okay. Okay, well, the first one seems to be a very good demonstration of the definition of a circle. Okay. All right, so it says in triangle ABC, angle C is 90 and AB equals to 12. So that just means that it's a right triangle with angle C and the hypotenuse is 12. And you have the two squares are connected outside a triangle and they all lie in a circle or whatever. Okay, so it should look something like this. And then all these points are on a circle like that. So if this is A, this is B, this is C, AB, X, Y, AC, W, Z. All right. And so you're given that everything is on the circle and that's it. What's the perimeter of the triangle? So the way you would solve the problem to find the perimeter of the triangle, that means you have to find one of the sidelines AC or BC because you know AB and you have a right angle. So you can use the Pythagorean theorem once you know one other sideline. And basically, there's a key insight to the problem here. And it's that, well, I wrote it here. The center of a circle is intersection of the perpendicular bisectors of the chords in the circle. So I kind of talked about this earlier with the circumcenter and the intersection of perpendicular bisectors. It doesn't necessarily have to be for an inscribed triangle, just for any chord within the circle. And the idea is that the intersection of the bisectors of ZW and YX or XY is going to be the midpoint of the hypotenuse of, or the midpoint of AB. And the reason why this is the case is because you have the intersection, not the intersection, the perpendicular bisector of XY is obviously going to be the midpoint of XY, and since it's perpendicular to XY, it's going to be parallel to AY and BX because it's a square. So it's like the line of symmetry of the square, which horizontally. So obviously passes through the midpoint of AB as well. And then for WZ, it's for the same reason going to pass through the midpoint of AC. And we also know from similar triangles that if you connect these two midpoints, the ratio of the sides formed here, you can see here, are going to be half of their respective sides. So since there's a common angle, that means that these two triangles are similar, so that this line between the two midpoints is parallel to BC. So if it's parallel to BC, that means that it must be perpendicular to AC. So it's perpendicular to AC and it intersects the midpoint, it must be the same line as the perpendicular bisector of WZ. And these two lines intersect, we know, at the midpoint of AB. So that means that the midpoint of AB must be the center of the circle. And from here, you can simply solve by finding the radius in two different ways. Like so, if you connect the center to Z and Y, you'd have Y is equal to, since this is perpendicular, you'd have Pythagorean theorem. This midpoint is going to be 6, since sine squared is 12. So Y is equal to 6 squared plus 12 squared, or the radius, I should say. That makes more sense. The radius equal to square root of 6 squared plus 12 squared, or the radius squared is that. And you also have, it's also equal to WZ, or 1/2 WZ. Let's just call AC ABC, X, and Y, just for the variables, I guess, since we need them. WZ is going to be half of Y, and W to the center is going to be WC, which is going to be equal to Y, plus X over 2 squared. All right, and basically, since X squared plus Y squared is equal to 12 squared, The idea is that you have now two equations and two variables, and you can now solve for x and y individually, and then simply find the perimeter by adding everything together. So yeah, that would be the problem. I'm not gonna like solve this because we're not gonna completely solve it, since after this it's no longer geometry, it's simply just solving an algebra problem, and I don't really have the time to do so. So again, if you do want to complete the problem on your own, you can. You check your work from here. The problem is right up here. And again, I think it's more important for these problems to figure out the method and how to approach the problem, rather than like how to just crunch the numbers and finish the problem. So again, like just being able to spot how you would do the problem is more important than being able to solve it completely. All right, so I did go over that one a little bit fast. So I think it would be helpful if you guys wanted to review this on your own. And that's all I have to say for that problem. All right, let's see, which one do I go next? I don't really want to go over this next one, so let's do this one. This one is quite simple. A triangle with side length and ratio 3, 4, 5, inscribed in a circle with radius 3, was area of the triangle. This one is really just testing your knowledge of circles, kind of, and triangles. And the main point is that 3, 4, 5 is the right triangle. So that means since the ratio is 3 to 4 to 5, it's going to be a right triangle no matter what the side length is, because of similar triangles. So we're just going to be inscribing a right triangle into a circle. And the side lengths are going to be in the ratio 3 to 4 to 5. And the main point here is that since this is 90 degrees, the angle of the arc it faces must be 180, so it must be half of the circle. This means that the hypotenuse of the triangle is going to be the diameter of the circle. And the diameter is just twice the radius. So from there, you know the radius is 3, so that means the entire diameter over the hypotenuse of the triangle is 6. And it's easily just find the area of a 3, 4, 5 triangle where the hypotenuse is sine of 6. So again, the main point of this problem is to recognize that if you have a 90-degree angle inscribed in a circle, it must be facing the diameter. And this is true for any right triangle inscribed in a circle. And it is one of the most commonly used things when it comes to that. So yeah, I think this problem. We know the ratio of the areas of similar triangles is going to be the square of the ratio of the side lengths. So the area of a 3, 4, 5 triangle is going to be 6. And you can get that by, well, 3 times 4 divided by 2. So we know that the area of this triangle must be 6 over 5 squared times 6. And that's it. So we're just using the ratio of the side length squared. All right. And I think it's 216 over 225. All right. If anyone has any questions, just not 225, it's 25. All right. So if anyone has questions about any of this, feel free to ask. But anyway. Okay, so how did I find the area? Basically, the idea was using similar triangles. And since we know the ratio is 3 to 4 to 5, that means that this triangle right here, it must be similar to an actual 3, 4, 5 right triangle. And this is going to be your most commonly seen example of like Pythagorean triple of integer sides. So if you ever see 3, 4, 5, immediately think a right triangle. And so we know that these triangles are similar. So I wanted to use how the ratio of similar triangles' area is equal to the square of the ratio of the side lengths. So the area of this similar triangle, or the 3, 4, 5 triangle, is going to be base times height over 2, which is going to be 6. So 6, and then this is the ratio squared, times 6 squared over 5 squared is 216 over 25. And just want to mention, if you don't want to do that, that's fine as well. You can simply just find the other side lengths. Since if this is 6, the ratio is going to be 5 to 6, so, or 6 to 5 in this case. Then you can just simply find the other two side lengths are going to be 18 over 5 and 24 over 5. They're just going to be 6 over 5 times 3 and 6 over 5 times 4. And then from there, you can just do base times height and divide by 2. That also works. So either way, use similar triangles, you can find the area of this triangle. All right. Moving on. All right, I think I'm gonna. All right, let's do this one. Again, if you do want to do the prompt that don't get to on your own, that's fine as well. You can always check it by yourself. So with this one, we are given just a triangle ABC that has one side is twice of the other, and it might be easier just to draw this. ABC is twice, so AB is twice of AC, and D and E are on AB and BC, such that angle BAE is equal to angle ACD. Okay. So it should look something like this. Angle BAE, angle ACD. All right, and you say F is the intersection of the segments AE and CD, so that CFE is equilateral. What is angle ACB? All right, I should draw this better. But basically, this can be your diagram, and CFE is equilateral. And we're given that angle BAE equals angle ACD, so I should mark that. That's this angle and this angle. And now we have to find angle ACB. So basically, this is going to be an example of an angle chasing problem. I'm actually going to draw a slightly more accurate diagram, where if we start from the equilateral triangle and kind of just, I don't know, with equilateral triangles, you can find that everything is 60 since they're all equal. And we have this angle and this angle are the same. So how do we go about this problem? Usually, when you have given one angle as equal to another angle, but you're not given the length, you just use a variable. And I think we're going to use angle x, just because x is cleaner to use, I think. Doesn't really matter. So from there, you just label kind of everything that you know. Oh wait, I forgot. Oh, I forgot to mention that thing. I forgot to mention that AB is twice of AC, and that is going to be useful somewhere. All right. So first off, what you should do with these problems is just label as many angles as you can And yeah. So first off, we have this is 120. Well, these are all 120 because, well, they're all supplementary to 60. And this is 120 here. So since all the angles in the triangle up to 180, we know that angle CAE is equal to 60 minus x. And this is because 60 minus x plus x plus 120 is equal to 180. So what this means is that angle A is equal to 60 because angle CAE equals 60 minus x, and angle BAE equals to x. They add to 60. And now here is where AB equals to 2 times AC comes in. We know the ratio of this is 2 to 1. And what this is really asking you is to see if you can recognize what this triangle is. And the idea behind that is once you see that this angle is 2 and this is 1, you should know that angle ACB is 90 degrees. And the reason why is because for a triangle that's for a 30, 60, 90 triangle, as these are called, they have the property that the ratio of the side length of the hypotenuse is 2 to 1 for this one of the for a leg next to the 60 degree angle. And this works because if you like flip it over this height, you get this is 30 and this is 60. So now you have an equilateral triangle. You see, 30, 60, 90 is just half of an equilateral triangle. And since all the sides are the same for an equilateral triangle, this like point here would be kind of the midpoint. So the sides would be half of the hypotenuse. So this is why the 2 to 1 ratio is what is related to a 30, 60, 90 triangle. So once you would see it's 2 to 1, you should recognize that angle ACB is 90. And if you don't, then there really isn't a way you can kind of solve the problem. All right. So the things I want to mention for this problem is angle chasing, where you usually have one variable angle and you just find other angles from it, and maybe you'll find something useful. And two, use everything you're given in the problem. So this side length AB equals 2 times AC doesn't seem very useful at first, since you don't really know any of the other side lengths or anything like that. But eventually it does become useful. So yeah, for these problems, just make sure you keep track of what you're given and see if there's anything you don't need or you didn't use, since you'll probably will need it eventually. All right, so those are my main takeaways for this problem. And yeah, I think we could probably do like one more. So all right, so again, I do want to mention this is a challenge problem for this week. And it's kind of cut off, but this is a diagram. So again, it's going to be kind of the same thing as last week for the challenge problem, so you can do it if you want. You don't have to. But yeah, I think I'm going to do this problem right here, which is in the given circle, diameter EB is parallel to CD, and AB is parallel to ED. And the angles AEB and ABE are in the ratio of 4 to 5, what is the degree measure of angle BCD. And I like this problem a lot because it's just a kind of really nice way of doing, or not doing, but like seeing how cyclic quadrilaterals are pretty useful. So the only thing you're really given at first is the ratio of angle AEB and ABE are 4 to 5. And what this tells you, since BE's diameter, is that angle A is 90 degrees for one, since it's the angle facing diameter, and angle ABE and AEB are going to be 40 and 50 respectively. And this is because they add up to 90 and the ratio is 4 to 5. So it has to be like that. And next, we have to figure out a way to incorporate our cyclic quadrilaterals. And basically, we can use the fact that EB is parallel to CD and AB is parallel to ED. So Actually, I don't actually think the CD is called EB is completely relevant. Anyway, that's not really part of the point. But like basically, since AB is parallel to ED, this angle is also 50. And we know this since they're like opposite interior angles like this. So it's written in the parallel line thing. These two angles are equal. Yes, and now from cyclic quadrilaterals, we have this quadrilateral BEDC is cyclic. All 4 points are on the circle. That means opposite angles add up to 180. So angle BCD is just 130, and that's it. So yeah, a few things you want to note is that one, you don't actually need this diameter is parallel to CD. This works no matter where C is on this arc. But yeah, so that's really it for this problem. It's just cyclic quadrilaterals and just how powerful they are. So yeah, it's 8 o'clock now. So I guess we don't have that much, we don't have any time really. So I guess we did some problems. There are still some problems left. I think they're all very nice problems. So you should do them if you get the chance. And again, if you do not figure out how to do them, you can always look up their answers and just read over it and I guess learn from that. So yeah, I think that'd be it for this week. If you do have any questions or anything like that, you can stay on and like ask me about it. But other than that, everyone can leave. All right, so I guess you have a question about the first question. So, okay. So you're asking why the center is going to be on the sides of the triangle, right? So last week we talked about interior angles. So for any circle, we have an angle that faces a chord. This is going to be equal to half of the measure of this arc. So basically, each angle like this will be half the angle of the arc, and we define the angle of the arc to be the angle where from the center, like this angle right here, is equal to the angle of the arc. So like we have the entire circle is 360 degrees. So that like whatever that measure of the arc is just like that part of the 360, so to speak, right? So with this problem, we're given that this angle that's inscribed is 90 degrees. And when it's 90, that means that this arc here is 180 because it's has to be twice of this inscribed angle. So it has to be 180 degrees. And then once you know that's 180 degrees, then that just means that this hypotenuse must be the diameter of the circle. And then from there, once you know the diameter, then the center, it must be the midpoint of the diameter of any diameter. So from there, that's how you'd figure out that that's how the center is on that line. So does that make sense? Okay. okay, wrong question. 2015 10 number 19. Wait. I'm sorry. I thought you said the first problem. Okay, so actually that was this problem right here. Oh, my bad. This one, I guess this one was a bit more complicated, where I wrote right here important concepts. The center of a circle is the intersection of the perpendicular bisectors of the chords. So what I'm saying is that for any circle, and you draw any chord, if the perpendicular bisector of the chord, which is just a line perpendicular to the chord and pass through the midpoint of the segment here, must pass through the center as well. And the idea behind that is that any triangle you make with this chord and the center is going to be isosceles because all the radii are the same. So what that means is that these angles are going to be the same. And when you draw like the height of an isosceles triangle, it also is the midpoint. So like these lengths are going to be the same for like an isosceles triangle. I think, do you understand like that part where the height, when you like drop the height for an isosceles triangle, it goes to the midpoint? And the reason behind that is simply because we have these sides are the same. This height is going to be the same for both triangles, and like it's symmetric basically. So since it's symmetric, they have to be like all equal. So like after like you get this, you know that every single like for any chord on the circle, its perpendicular bisector must pass through the center. And now, so if we take two chords, we have them right here, WZ and XY. Then the perpendicular bisector of this chord must also pass through the center. And now we know two of these perpendicular bisector lines. And these two lines can only intersect at one point, since two lines can only intersect at most one point. And that means that the point they intersect has to be the center of the circle. There is no other point they intersect, and there's only one point that satisfies both of the conditions for each chord. So that point has to be the center. Then once you understand that, you simply just connect your perpendicular bisectors. And it's very convenient that everything's a square. So all these perpendicular bisectors are going to be parallel to the side lines. So like if it's perpendicular to XY, it's also perpendicular to AB. And since it bisects XY, it must also go to the midpoint of AB. So now you've established the midpoint of AB is going to be on this line. You can go over to WZ and simply put, you can kind of find, if we just take out the square and the triangle, this line right here will pass through the midpoint of this hypotenuse and of this side, like that. So like the two perpendicular bisectors will both go through this one point. It's the only point they both go through, so it must be the center. So does that make sense? All right. So if anyone has any more questions, feel free to ask.